Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on a case study for modeling heteroscedasticity. In this lesson, I'll continue an analysis of exchange rates with a modeling, a joint ARMA-GARCH modeling for all three currencies. Recall that the selected orders for ARMA for the Euro-USD exchange rate difference time series were an AR order equal to 6 and an MA order equal to 3. Assuming the ARMA orders fixed for the conditional mean, we now select the order of the GARCH model for the conditional variance, assuming an ARMA-GARCH joint model fit. Note that this time I'm fitting the orders on the training data, which is a subset of the initial time series without the last months of the time series, July and August. The last 2 months of data are now for testing the prediction accuracy of the model. To select the GARCH orders, we loop through all combinations of M and N orders, taking values between 0 and 3, fit the ARMA with orders 6 and 3 and GARCH model with orders M and N, and then select the orders M and N for the model with the smallest BIC. Note that I am using here the BIC, or the Bayesian Information Criterion, to select a parsimonious GARCH model, which is preferable when fitting an ARMA-GARCH joint model, which is already very complex. The selected orders for the GARCH model for the conditional variance are M equal to 1 and N equal to 2. We'll continue with refining the orders for ARMA, fixing the orders for GARCH. Here, I'm selecting P and Q for the ARMA model for the conditional mean, but this time fitting a joint ARMA-GARCH model. Recall that fitting ARMA-GARCH simultaneously will also mean determining both the ARMA and the GARCH order simultaneously. Neither the conditional mean nor the conditional variance model can be estimated consistently if taken separately. Joint estimation would typically be more efficient, and that is why it is preferred. Unfortunately, the task of jointly determining the ARMA and GARCH orders is difficult. Thus, here we select the orders of ARMA and GARCH separately, but fine-tuning the order selection. We assume that the orders of GARCH are as selected in the previous slide and allow only the ARMA orders to vary within the range 0 to 6. The selected orders are now AR equal to 0 and M8 equal to 0, suggesting that the condition mean of the difference process of the Euro-USD currency exchange rate does not depend on time when jointly modeling the conditional mean and the conditional variance. I will note here that depending on the solver, there may be combinations of the orders for which you will get an error message, which is due to the lack of convergence of the numeric algorithm. If that is the case, the for loop will stop and you have to restart the search, excluding the combination of orders for which convergence is not attained. This was the case for P equal to 1 and Q equal to 2 in this model selection implementation. Last, assuming the ARMA orders fixed to the values provided by the last model selected for ARMA, now we fine-tune the orders of GARCH by selecting again among all combinations of M and N, taking values between 0 and 3. The orders selected are M equal to 1 and N equal to 2, thus with no change from the orders selected when the ARMA orders were 6 and 3. For all three currencies, while we start with the complex ARMA model, the selected ARMA, after accounting for the joint modeling with GARCH for modeling the conditional variance, reduces to an ARMA 0 0 for the first two currencies and an ARMA 1 0 for the third currency. There is also no improvement in the order selection of GARCH when considered the more complex ARMA versus the less complex ARMA, and that's for all three currencies. We'll only compare two models. Next, I compare the two models using multiple information criteria. Again, for the Euro-USD exchange rate time series, the two models to be compared are ARMA with order 6.3 and GARCH with order 2.1, and the ARMA with order 0.0 and GARCH 2.1. The R code in this slide is for the comparison of these two models. It will be similar for the other two currencies except for the ARMA and GARCH order specification. These are the R outputs for the comparison of the information criteria for the two models for each of the three currencies. Across all currencies, both models perform similarly, suggesting that the less complex model with low AR and MA orders for the conditional mean would perform similarly as the more complex ARMA with high AR and MA orders. In summary, in this lesson, I illustrated the implementation of the joint ARMA-GARCH model for the three exchange rates. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial System Engineering. This lecture is on a case study for modeling heteroscedasticity. And in this lesson, I will continue the analysis of the exchange rates with a focus on the prediction. For this example, we predict the currency for the last 2 months of the time period, the months of July and August 2017. The predictions are one lag ahead, obtained on a rolling basis. That is, we loop through all the time points to be predicted. We set the past data as being the time series observed up to the time point at which a prediction will be made. Then, fit the ARMA-GARCH model with the specifications provided for the two models in the previous lesson, but this time the model is fitted on the time series observed up to the time point at which a prediction will be made. Thus, with each prediction, the training data set changes. After the model fit, the one lag prediction for both the mean and the variance are obtained using the UGARCH forecast R function. We thus obtain predictions at each time point within the time period of the 2 months. We apply the same code for both models and for all three currencies. The prediction accuracy measures for the forecast of the mean for the different Euro-USD currency time series are on this slide. The measures are computed for both models. The first model being the ARMA with order 6.3 and GARCH with order 2.1, and the second model being ARMA 0.0 and GARCH 2.1. The prediction accuracy is lower for the second model across all measures, indicating that the model where the conditional mean does not depend on time performs better than the more complex model for the conditional mean. As pointed out in previous lectures, generally the precision measure is most appropriate in comparing prediction accuracy within this type of modeling. The smaller this measure is, the more accurate the prediction is. The measure is approximately 1.04, indicating that the proportion between the variability in the prediction versus the variability in the new data is 1.04. Thus, the variability in prediction is similar to that in the data. These are the prediction accuracy measures for the mean prediction for the Brazilian real USD dollar currency exchange. Similar results are noted as for the Euro USD currency, although the prediction accuracy is slightly worse for the Brazilian real currency than for Euro. These are the prediction accuracy measures for the mean prediction for the Chinese yuan USD currency exchange. Again, similar results are noted, but the prediction accuracy is slightly worse than for the other two currencies. This is the R code for comparing the mean predictions to the observed time series by overlaying the predicted means for the two models to the observed time series. Here are the plots. The predicted means are close to 0, with some variations in the predictions performed with the more complex ARMA-GARCH model for the Brazilian real and Chinese yuan currencies. Note that the mean predictions do not capture the variations in the different time series, since these variations are due to the variance, not to the mean of the process. Last, we'll take a closer look at the predictions for the volatility. The comparison now is between the squared time series data and the predictions of the conditional variance or volatility. The plots for the three currencies are here. The volatility is not well captured by the forecasted conditional variance for the euro currency, but it is captured much better for the other two currencies, particularly much better for the Chinese yuan. To conclude, we have seen that a joint ARMA-GARCH model performs differently across different time series. Note also that the volatility for the euro currency was smallest among the three currencies, while the predicted volatility captures much better the condition of variance in those time series with higher volatility. The GARCH model introduced in this lecture provides the basis for the development of many other extensions of heteroscedasticity models. In the last lesson in this lecture introducing GARCH models, I pointed out several other extensions such as exponential GARCH or integrated GARCH. These extensions and others provided on this slide are meant to deal with different distributions of the volatility, for example, asymmetrical response to positive and negative shocks, large or small vortices, meaning more or less heavy tail distributions, among others, or nonlinear relationships with the past condition of variance. The good news is that many of the models are already implemented in the R statistical software, and most of them can be applied through the UGARCH spec and UGARCH fit functions from the RUGARCH library used to fit the joint ARMA-GARCH models. In order to specify the other model types, you'll need to specify the model into model options of UGARCH spec. The default is the GARCH model. Let's compare these models using the difference currency exchange rate time series for the Euro USD, US dollar. Because we have learned from the joint modeling of the conditional mean and conditional variance that the conditional mean does not vary with time, I focus here on the modeling of the conditional variance. The code for forecasting the conditional variance is not different from the one provided in the previous lesson and thus not provided here. This is the plot of the predicted variance along with the observed squared time series shown in black. We see that the other models for heteroscedasticity have not improved the estimation of the volatility since none of the predictions capture the ups and downs in the squared difference time series. It's possible that such variations are due to randomness alone rather than serial correlation. I'll note here that running the forecasting code with all the 5 models and for a large number of time points at which we obtain predictions took more than a day of computational time. Such models are computationally expensive, and his real-time predictions are not possible even using more efficient computations. This is one drawback in the implementation of heteroscedasticity models in general. This lesson concludes the analysis of the exchange rates for US dollar versus 3 currencies. And I concluded this lesson with a comparison of the predictions. Thank you.